In this video, we are going to talk about intermolecular forces, which are also commonly referred to as IMFs. So, intermolecular forces are the attractive forces between particles. You can think of those particles as the molecules in a liquid, solid, or aqueous phases. And these IMFs are what hold those different molecules either close together or not. IMFs are weaker than actual bonds. They are not bonds, and they will affect physical properties such as surface tension, melting point, and boiling point. They can also affect things like viscosity, the ability for a liquid to flow, or vapor pressure, the pressure right above a liquid. So these are just some examples of the types of properties IMFs can affect. Surface tension is a measurement essentially of the IMFs in a liquid molecule. So surface tension is a measurement of how much energy or the amount of force is needed to separate two liquid molecules. So in this example, we have all these different water molecules, and these lines here represent the forces that hold those different water molecules together. So surface tension measures how much energy is needed to separate these water molecules. How tightly they're bound together or they're attracted to each other is going to determine how much energy is needed to break them apart. Surface tension is also the reason some liquids are able to form these spherical drops. And in forensic chemistry, this can be really important for blood spatter analysis because you can tell the way the liquid is dropping based on the shape it makes after it drops. Dropping straight down is going to give a different shape than dropping at a diagonal. All right, in this class, we're going to talk about three different types of IMFs. The first one we're going to talk about is London dispersion forces. Now, don't be alarmed. Sometimes these are just referred to as dispersion forces. Sometimes they're just referred to as London forces. They can also be referred to as LDFs, which are London dispersion forces. They're kind of all used interchangeably. But London dispersion forces are known as the default IMF. And they're known as the default IMF because they're literally present in all molecules. So they are present in all molecules. They are also the weakest IMF. They are the weakest of all the IMFs that we're going to talk about in this class. You can determine if something only contains dispersion forces if they are non-polar molecules. So they are the dominant IMF in non-polar molecules. We'll move that over and write dominant IMF in nonpolar molecules. So what that means is they are the only IMFs that are holding those two molecules together. And they work by creating an induced dipole. And this induced dipole, what it does is it affects the shape of the electron cloud. And it is a temporary induced dipole moment. So we have this induced dipole interaction, and this is how easily the electron cloud can be distorted or changed. So if a nonpolar molecule is in a presence of a polar molecule, then it can induce a shift in the electron cloud. So the electron clouds are going to be randomly and unevenly distributed instead of more uniformly distributed. It's going to increase with increase in size. So the larger the molecule is, the stronger the IMF is. And you can see that in this table here where we have all of the different halogens. And as we increase in size, the melting point is also increasing. The second type of IMF is the dipole-dipole force. This force is a moderate IMF. So the London dispersion forces are the weakest of all the forces. The dipole-dipole forces are fairly moderate. They are not present in all molecules. They are only present in polar molecules. They are the dominant IMF. In polar molecules. So polar molecules do not have an induced dipole area. They don't have an induced distortion in the electron cloud. It's always there. So in this example here, we can have a partially negative end of the molecule and a partially positive end of the molecule. And the way they line up is where the partially negative end of the molecule will be attracted to the partially positive end of the molecule of another molecule. So this attraction that happens right here, that is the IMF. That is the force, the attractive force that is holding these two molecules together. A common example of that is something like formaldehyde. When you have formaldehyde, which is CH2O, we can look at the Lewis structure. And we have a polar bond between the carbon and the oxygen. So the oxygen is going to have a partially negative sign. The electron cloud is going to be distorted and move towards the oxygen, whereas the carbon is going to have a partially positive sign. So if I have another formaldehyde molecule, the way it lines up is the oxygen is going to be flipped so that it can be attracted to the carbon. And then the carbon is going to line up so it can be attracted to the oxygen. And the partially negative sign on the oxygen is what is going to attract the carbon from the other formaldehyde to the oxygen, and that is the IMF. If your atom is more partially positive or more partially negative, you can think of it is just really increasing that magnetic attraction. So you will have a stronger IMF. So this dipole-dipole force is going to be the attraction between oppositely charged regions of the neighboring molecules. When we're looking at solubility of molecules, of liquids, we look at it in terms of like dissolves like. So a polar molecule dissolves a polar molecule. And nonpolar molecules will dissolve nonpolar molecules. So London dispersion forces are your weakest IMS. Dipole-dipoles are your moderate IMS. They're found in polar molecules. They're the dominant IMF in polar molecules. And just to be clear, polar molecules also contain London dispersion forces because those are the default force. However, the dominant IMF holding the two molecules together is the dipole-dipole force. Finally, we have what is called the hydrogen bond. This is very important. A hydrogen bond is not an actual bond. It is still an IMF, which means it's an attractive force between the two molecules. However, it is the strongest IMF that we are really going to be talking about. And hydrogen bonding only occurs in certain instances. So it happens when you have hydrogen directly bonded to fluorine, oxygen, or nitrogen. So I like to think of hydrogen bonding as very fun. Get it? Right? FON. It's very fun. Now, what's important about this is the hydrogen has to be directly bonded to the fluorine, oxygen, or nitrogen. If the hydrogen is not bonded directly to the fluorine, oxygen, or nitrogen, then you don't have the capability of hydrogen bonding. And that is because the difference in electronegativities is not as high, so that attraction is not as high. If we just look at the chemical formula of formaldehyde, you might think, oh, this has hydrogen bonding. CH2O, because it has hydrogen and oxygen. However, when you look at the actual Lewis structure, you can see these hydrogens are not actually bonded to the oxygen. So this is not capable of hydrogen bonding. However, it's still a molecule that is polar, so it does have dipole-dipole forces. Water is a great example of a molecule that has hydrogen bonding because you have a hydrogen directly bonded to the oxygen. So that means the partially negative side of my oxygen is going to be even more partially negative compared to that of a polar molecule. And the hydrogen is going to be even more partially positive. So if we have another water molecule, it's going to line up so that the oxygen of the other water molecule is going to be attracted to the hydrogen of the other molecule. And this attraction right here, like we said with the other one, that is the IMF. But because these are that much more positive and more negative, then this bond, or sorry, this hydrogen bond that occurs, which is not an actual bond, this force that occurs is a lot stronger. So if I draw the rest of my water molecule, the hydrogen is going to line up like so, and it's going to be this really strong attractive forces, and we have the ability of hydrogen bonding in multiple areas of the molecule. So let's look at the different types of IMFs that can be found in the following molecules. Methane, CH4, only contains carbon and hydrogen. I know that hydrocarbons are always nonpolar. So since this is a nonpolar molecule, it is only going to have dispersion forces. NH3 has both nitrogen and hydrogen. There's no other atoms in it, so the hydrogen must be directly bonded to the nitrogen. So it is going to contain hydrogen bonding. Now, since it has hydrogen bonding, that also tells me that it is a polar molecule. So it's also going to have dipole-dipole. And since London dispersion forces are the default IMF, it's also going to have London dispersion forces. Now we looked at formaldehyde already, and this is the one I warned you about. It looks like it is going to have hydrogen bonding based on the chemical formula. However, like we saw with the Lewis structure, we don't actually have a hydrogen bonded directly to our oxygen. So it is not capable of hydrogen bonding. However, it's still a polar molecule, so it's still going to have dipole-dipole forces, and it's going to have the London dispersion forces as well. Sometimes you really can't tell from the chemical formula what type of interactions the atoms are going to have. So it can be very useful to draw the Lewis structures for these compounds. HCN, if we draw the Lewis structure for that, we can see that it is polar. It does have hydrogen and it does have nitrogen, but again, the hydrogen is not directly bonded to the nitrogen. So this is a polar molecule. It does not have hydrogen bonding. So the different IMFs present are dipole-dipole and London dispersion forces. You can go ahead and try the second set of problems. Send me the answers and I will give you extra credit on your quiz.